Welcome back once again to a tutorial on the BJTs, and of course, as you can see, this is again we're continuing from our previous tutorial on the BJT operational modes, and well, one more operational mode to go over here. So yeah, you guessed it right, that's the CC, or the common collector mode, that we're going to discuss in this particular tutorial. Okay, so the common collector mode that we're going to talk about over here, as I said, or rather mentioned in the previous tutorial, if you all would remember that, well, whatever terminal we just make common, that is of course connected to the ground terminal as such. Okay, and all the that particular terminal is just, well, becomes a common terminal for connection between the other two that are not mentioned in its name. Okay, so let's not just waste time over here. We're just gonna be bringing up the circuit concerned. Okay, so there you go. There's our diagrams, and we can just see that in the case of both the PNP and the NPN type of the BJTs, both in both the cases, the collector terminals have been grounded over here, as you can see. Well, yeah, as also it's visible in both the diagrams over here, that we've got, well, two loops in both the figures. Okay, so the one including the base and the collector terminals on the left of each one of the PNP and the NPN ones are the input loops. I'm just going to write it down over here. So this is, of course, is the input loop, and on the right, the loop concerning containing the emitter, collector, and this voltage source V2 is obviously, well, regarded as the output loop. We're going to take our output from this part of the circuit. Well, and it's the same case for its NPN type counterpart. Okay, so that's the basic structure of what the BJT would be like to operate in the common collector mode. Okay, so now the common collector mode obviously has, well, two types of characteristics which we are going to study in this particular tutorial. So let's just start with the input characteristics over here. So I'm just going to write that down over here. So this is part A. We're going to study the input characteristics of that of the common collector mode. Okay, so there you go. So in this input characteristics study that we're just going to make over here, we're just going to study the variation of the base current with respect to collector base bias voltage. Okay, so I'm just going to write that down over here. Okay, so this is exactly what we're just going to do over here, and in order to do that, we're going to set up an experimental version of these circuits that we've just, well, drawn over here for both the PNP as well as the NPN type counterpart. Okay, and just keep the base current and the collector base bias voltage variable. Okay, so I'm just going to show you the circuit right over here, so kindly just hold on for the second. Okay, so here's our experimental setup for the input characteristics. Okay, so what we're going to measure here is we're basically going to measure the collector base bias voltage that's going to occur right over here. Okay, I'm just going to write it down, and of course the input base current, that's IB, and same goes for same goes for the NPN counterpart of this BJT over here. So there you go, that's IB, and of course here is VCB. Oops, I made a mistake. Okay, I just gotta rectify that. I'm just gonna turn the arrow in a different direction. I'm gonna turn it opposite. Okay, I'm just kind of hold on with me for a second. Okay, yep, there we go. Now that's okay. Fine. So our experimental setup being here, we're just gonna go forward and study the variation of IB versus that of VCB. Okay, but before we do that, let me just tell you, we're just gonna keep here the VCB variable. Okay, so in order to do that, we're just going to keep V1 over here. That's the voltage source for the input loop over here. We're going to keep V1 as a variable voltage source. Okay, and of course, keeping V1 variable, we're going to get IB variable as well. Okay, I'm just going to write it down over here, and as well as VCB. Okay, Same goes for VCB. And now we're just going to keep the V2, that's the voltage source at the output loop over here. We're just going to keep that at a constant value. So we're just going to keep V2 constant. Okay. Yeah. Now that's done pretty much. And with that, if we just go forward and well measure the variation between the that of the base current and that of the collector base bias voltage over here, we're gonna get a graph that would look something like these graphs that we have over here. Okay, so on the left we have the input characteristics in the common collector mode for the PNP type of BJT, and we have on the right for its NPN type counterpart. Okay, so unlikely of what we just saw in the previous tutorials about the common base and the common emitter mode, these input characteristics have a completely different story to tell. So you can see over here that if I just well write down an equation which would just facilitate your understanding over here, you'll have already seen from the previous tutorials that for a particular BJT, the total voltage falling across that of the falling across that of the collector to emitter terminals is obviously equal to the voltage that occurs between that of the base and emitter terminals plus that of the voltage drop occurring between the collector to base terminals. Okay, so now if we would well, obviously, if we would just you know make VBE the subject of formula from this particular equation, then we're supposed to get, well, VBE is equals to, well, VCE minus that of VCB. So from this particular equation which we are getting over here, okay, if we just gonna keep well, if we're just gonna, well, go on increasing VCB so that, well, VCB tends towards VCE, if we just, well, go on increasing VCB so that its value, well, becomes equal to that of VCE at some particular time instant, then over there we're going to get, well, VBE equals to 0. So then under this particular circumstance, VBE will tend towards 0. So if we just keep VCB equals to VCE, we're going to get VBE, that's the base emitter voltage, we're going to get it as equals to 0. And whenever the base emitter voltage is 0 or approximately 0, the transistor, or rather the BJT, would turn off because it requires approximately a voltage of 0.7 volts minimum in order to turn on the BJT, so that it'll so that this particular voltage level is just able to forward bias the emitter junction present in the BJT. So this is exactly the story told by the input characteristics of both the PNP and the NPN type BJTs for the common collector mode of operation. We can see over here that, well, if let's just take the NPN type of BJT for the reference. So if we're going to keep the collector to emitter voltage at, let's say, 5 volts, so if we're just going to keep well, this particular voltage V2 fixed at, let's say, 5 volts, then we can see over here that, well, as we can just go on increasing the collector to base voltage, okay, if we just go on increasing V1 over here, then it is quite obvious that the collector to base bias voltage would go on increasing. So under that circumstances, what happens is that, well, the base current goes on decreasing until it just comes down to, well, 0. Now, why does the base current go down to 0? It's because if the base emitter terminal right over here is in forward bias, then there's no carrier coming from the emitter towards the base. So no carriers coming from the emitter towards the base means there's no recombination current, which constitutes the base current over here. So that's exactly what the story is, as we can see over here in this particular mode of BJT operation. So we have here, well, 3 types of curves for different values of the collector to emitter voltage, and we can see in all the 3 cases, whenever VCB, that's the collector to base bias voltage, whenever it's equal to that of the VCE, or rather the collector to emitter voltage as mentioned over here, the base current just drops down to 0. So it's the same case for both the types. So that's exactly what we have from the input characteristics over here. And now if you just quickly take a look at the output characteristics as well. So I'm just going to write that down over here. So that is part B, the output characteristics. Okay. So just kindly hold on with me for a second. Okay, so in case of the output characteristics, what we have over here is that we're just going to study the variation of the emitter current that's represented by the symbol IE versus that of the collector to emitter voltage. Okay, so if we just go back to our diagram, that's our experimental diagram over here. So of course for the PNP type, this would be the direction of the emitter current. Okay, and well, the collector to emitter, the collector to emitter voltage would be, well, taken in somewhat this way between that of the emitter and the collector terminals. And similarly, if we just look at the NPN type transistor, then in that case the emitter current would have a different direction. That's just the opposite of what we just see for the PNP type. And well, again, the collector to emitter voltage will be measured between that of the collector and the emitter terminals. So under this particular circumstance, okay, so under this particular circumstance of the output characteristics, well, we can basically draw a curve between these two quantities and their study their variation. So if we just draw a curve, we're going to get something like this. Yep, there you go. And so as you can see over here, we're going to get the output characteristic curves that are going to look something like this, as you can see. Well, these curves, if you would observe quite closely, you'll see that, well, they're quite similar in their shapes with that of the curves that we obtained for the common emitter configuration of the BJTs. So if we just going to take a look over here for the different types of curves for the PNP and the NPN type, we've just taken the components that just, well, the current components basically, that's the emitter current for the NPN type that just leaves the device. So we just taken that as a, well, as a negative quantity over here so that you can understand that the current just leaves the device. Well, in the case of the PNP type counterpart, it's just positive because it just enters. Same thing over here for the base currents. So that's just a, well, a sort of a way to understand the curves better. So you can see that, well, there are different curves for, well, different values of the base current that we are going to encounter over here. We can see that, well, as the base current just goes on increasing, the curves become higher, and well, of course, the amount of emitter current obviously, well, increases. So it's not quite, well, all that different from what we saw in the case of the collector, for that of the common emitter configuration of the BJTs. Okay, so these curves over here can also be, well, divided into three basic regions of operation. So here we have our, well, saturation region where it's quite natural. I'm just gonna write that down first. So here we have the saturation region for both that of the PNP as well as, as well as the NPN type of BJT being used in this particular diagram over here. So yeah, that's the saturation region. Just kind of hold on with me for a second there. Yeah, that's okay. So in this saturation region, as you learned in the case of the common emitter configuration, that, well, here both the collector and the emitter junctions are, well, forward biased. So the collector, the collector base junction over here is, well, not kept at a reverse bias. It's just, well, forward biased by a very little value, well, close to 0 volts. Okay, so that's the all the discussion for the saturation region. So we also have the cutoff region, which I'm just gonna shade it down over here. Well, there you go. So that's the cutoff region for that of the PNP type of BJT for the common collector mode. And over here on the right, we have the cutoff region for that of the NPN type BJT. So here you can see, well, for in the cutoff region, the base current is almost, well, kept at 0 microamps, Okay, and for that reason we're going to get a collector, I mean sorry, there an emitter current over here, which is quite close to that of the 0 volts. Okay, and apart from that we have the active region of operation that includes this middle portion over here. So there you go, in the active region. So the active region is that region of operation where the BJT is ideally operated and optimized to be operated in this particular region, of course. So in this particular region, that's the active region we're talking about, the emitter junction is kept at a forward bias voltage, while the collector junction is just kept reverse biased. While in the cutoff region, both of the junctions are kept at reverse bias, as you had seen back in the previous tutorial. So that just brings us to a close of the discussion over here for that of the common collector mode of operation for that of the BJT. So you can pretty much see over here. Now if we would just take a little more pain to compare or rather just compare the amount of emitter current that we receive for a given value of base current. Let's just take IB equals to 20 microamps over here, and we're going to get approximately about 2 milliamps of emitter current for a base current of about 20 microamps. So if we just take the ratio of the emitter current versus that of the base current over here, we can get 2 milliamps. That is of course so that is of course 10 to the power 3 times of that of, or rather let me just keep it this way, no problem. That's 2 milliamps over here, and if we're getting 20 microamps, so 20 and that's 10 to the power minus 6. So if we just calculate all this over here, then we're going to get about 100 times of multiplication factor which we're going to obtain whenever we just comparing the magnitudes of the base current and the emitter current. So we can see that this particular mode of operation does give us some sort of gain in the magnitude of the output current received from that of the emitter. So as you can see in this particular mode of operation, as we're just taking the output from that of the emitter terminal, okay, so in this particular mode of operation, we can obviously get some sort of current gain, which is about 100, and this particular factor is just expressed by the term gamma, which is just known as the current multiplication factor for that of the CC mode. So I'm just going to write that down over here. This is the current multiplication factor. Okay, yeah, there you go, factor for the CC mode. Okay, so with this particular data just given to you all, you can basically reflect upon it. We can just write that down over here as IE equals to gamma times that of IB. So we can just use this particular relationships in order to solve numerical problems on the common collector mode of operation. Okay, so that said, we just come to the end of a tutorial on the common collector mode of the BJT operation. So see you in the next tutorials that follow, and just kindly keep watching. So it's just going to be a short goodbye for now, and we'll see you next in the later tutorials. So goodbye.